This is second part of chapter 10. Let's start by reviewing a couple of things which we studied in the previous section of chapter 10. We had talked about some methods of preparation of alkyl halides from alcohols and also from NBS. So the first one is asking if you have a tertiary alcohol, how if you react it with HBr, right? So this is a tertiary alcohol, and if you reacted with HBr, what would be the product? So if you recall, in a tertiary alcohol, the OH can be substituted by Br. So the product of this first reaction would be a methyl group here and then a bromine here. Now this one is a primary alcohol, and if you treat it with SOCl2, which is thionyl chloride, you can again replace the OH with a chlorine. 1, 2, 3, 4 carbon atoms. I'm just going to draw the skeletal structure, and then you can replace the OH with a chlorine. So that's the product of B. Now with C, if you recall, when we have an alkene and it is treated with NBS, which is like a source of bromine radical, then the allylic positions are allylic hydrogens are substituted with bromine. So here the allylic hydrogens are the ones which I have highlighted in red color, okay? And if you recall, the allylic hydrogens are the ones that are substituted because the allylic radical that is formed is stabilized by resonance. Okay, so here all these 8 hydrogen atoms are exactly the same, so we can write the product with just one of the hydrogen atoms getting substituted by bromine. Double bond remains intact, do not change that, and then you can put a bromine atom replacing the hydrogen atom. So if you had placed the bromine here or here or here, it would be the same product, so it doesn't matter which hydrogen you can substitute with a bromine atom. The next one, final one, is a secondary alcohol, and then we are treating it with PBr3, and then again OH will be substituted by bromine in this case, so that would be a product. In the next question, we are asked to how you can synthesize these products that are given from alcohols, right? So what you will see, first look at it and see, okay, this is a tertiary alkyl halide, so we need a tertiary alcohol to produce this. So the tertiary alcohol would be a carbon atom, which is this one, right? That's my middle carbon atom with 3 CH3s, and then I have a OH. So if I take this and I treat it with HCl, right, that will give me the replacement of OH with a chlorine. So you need a tertiary alcohol reacted with HCl gas, and then you can substitute the OH with chlorine. Next one, you see it's a secondary alkyl halide. So the best way for producing this would be to take a secondary alcohol and treat it with PBr3. Okay, so we have 1, 2, 3, 4, 5 carbon atoms. So what I would do is take this compound, okay, and have an OH at the same position where the Br was, and then we have to make the correct structure, so there's a CH3 here, and then if you treat that with PBr3, that should give you the respective alkyl halide that's here. Another similar to that is this compound C, where you again have a bromine but at the primary carbon atom. So again, we do the same thing. We use a primary alcohol, 1, 2, 3, 4, 5, 6. So I'm just drawing the skeletal structure again, 1, 2, 3, 4, 5, 6. And then I have an OH here. And then at this carbon atom, I have a methyl group, right? I have to make exactly the same structure as given in this molecule, except that instead of the Br, I have a OH. Okay, and it's a primary alcohol. We have to create it from a primary alcohol, again treated with PBr3. And the last one here, we have a chlorine, and it's a carbon atom to it's actually a tertiary carbon atom, right? So the best way would be to take a tertiary alcohol. So 1, 2, 3, 4, 5, 6. Take a tertiary alcohol, 1, 2, 3, 4, 5, 6, and here we have a methyl group and another methyl group, and then we take a carbon atom attached to an OH, Um, Here we have another methyl group here, right? So this we take a tertiary alcohol and then treat it with HCl in order to give the respective alkyl halide. So this is how you can think back of how to what starting material you can use in order to produce these alkyl halides. Moving on to the next section, we actually did talk about Grignard's reagent, but just a quick review that Grignard's reagents are very versatile reagents because they can act as nucleophiles. Okay, they can act as nucleophiles and as bases. The general formula is RMgX. Again, R can vary between a primary alkyl, secondary alkyl, tertiary alkyl. It could be an alkenyl or an aryl, and again halogens, the X can be chlorine, bromine, or iodine. So what you need is take an alkyl halide, like for example if I take CH3Br, which is an alkyl halide, treat it with magnesium, then what happens is magnesium inserts between the carbon and the bromine atom, and you get the Grignard's reagent. Okay? Why they are acting as good nucleophiles? Because magnesium is a metal. It likes to push away the electrons towards the carbon atom, making this negatively charged. Magnesium becomes positively charged, and that makes this carbon atom nucleophilic in nature. It is also basic. That means if you treat it with a proton source, then it can behave as a base and abstract the proton from the acid. This is Victor Grignard. He actually was awarded a Nobel Prize for this really useful reagent that he synthesized, which we call it as the Grignard's reagent. This is an example again showing the really basic and nucleophilic nature of the carbon atom in the Grignard's reagent, which can act as a nucleophile and as a base. Here is an example where we are looking at the formation of a Grignard's, right? This is a Grignard's reagent, the one which I have circled here. And here we have a proton source, which is water, right? And water can provide proton. And even though it's weakly acidic, but since this carbon atom is powerful base, it can actually abstract this proton and then give this alkane, showing its acidic nature. Okay, sorry, its basic nature. Okay, so Grignard's reagent can behave as base as well as a nucleophile. Another type of organometallic, so these type of compounds, let me go back one step to show you that these type of compounds are called as organometallic reagents, right? These are called as organometallic reagents. Why? Because there is a metal attached to a carbon atom, right? So it's a direct attachment of the metal to the carbon. So this is how the bond is. So these are called as organometallic reagents. Another example of an organometallic reagent is this Gilman reagent, where the metal is now the copper atom. So how do we prepare a Gilman reagent is first you take, so here again it's a alkyl halide, that is the most important reagent. So we take an alkyl halide, again it could be any R group, so we have Rx, we treat it with lithium first, okay, 2 equivalents of lithium are needed, and the first step would be to create a organolithium compound, and it takes away the X atom. So for example here you can see that it's a bromobutane reacted with 2 equivalents of lithium. You get butyl lithium first, and then in the next step you take that butyl lithium or the organolithium compound and treat it with copper iodide. Okay, and then copper is divalent, so it takes up 2 of the R groups, and that product is what is called as the Gilman's reagent, which is a lithium dialkyl copper. Now in this case it's a dimethyl, but this can vary again. So if I write this as RLi and then you react it with copper iodide, then what you get is an R2, 2 of the R groups attached to the copper, and it's a kind of an ionic compound, and then one more molecule of lithium iodide is generated. This reagent which I have circled is what is called as the Gilman's reagent. It's a very useful reagent in order to increase the carbon chain. So we call that as coupling reactions. So for example, let's look at this one. Here first you generated a organolithium compound, okay, I guess we talked about before, and then reacted it with the copper to form the copper iodide to form the Gilman's reagent. Okay, so you have your Gilman's reagent, which is circled here, and then if you treat it with another alkyl halide, then you can actually extend the chain, which is what is called as the coupling reaction. Okay, so say for example, let me show you with a different example down here. Maybe say for example you have a CH3 to copper lithium, right? This is a very simple Gilman's reagent, and then if you treat it with another alkyl halide, say for example you have a CH3 CH2I, okay, then you can extend the chain where you can replace the iodine with one of the CH3 groups. So here is 2 carbon atoms, right? So you can actually make this into a 3 carbon atom from one of the CH3 groups here. So you can make it into a propane, and then your side products would be the one of the CH3 remains attached to the copper, so CH3 Cu, and lithium goes with the iodine. Okay, so see, you went from a 2 carbon atom chain here to a 3 carbon atom. So this is what is called as coupling. Look at another example. See, we have a aryl halide, which is a iodobenzene, and then you treat it with a Gilman's reagent. What has happened is you remove the iodine, and then one of the CH3 groups from here gets attached to the benzene ring. Okay, so you have increased the number of carbon atoms by one more because you added or you coupled one CH3 group to the benzene. So that's why these reactions are very useful, Gilman's reagents, so that we can use them in the coupling reactions. Just another example here of what can you write the products for this. So this one, if you look at it, it's a alkyl halide. All right, so let's make the skeletal structure of this. Sometimes it looks easier to understand. 1, 2, 3, 4, you have 4 carbon atoms, and then on the second carbon atom from here you have a Br attached, right? And then you're treating this with magnesium. So what you get is, remember, magnesium gets inserted between the carbon and the halogen. So your product here would be where it is an Mg, right? And then when you treat it with water, HOH, what happens is this carbon atom that's attached to the magnesium is the one that will take up the hydrogen, and you end up in formation of butane here. Okay, so you can, so this will go with MgOHBr, okay, and then you get the butane, and MgOHBr is your side product. Next reaction, it's a Gilman's reagent that's being prepared. So the first step would be where you have the lithium, or the organolithium compound, and then finally you form the Gilman's reagent. Okay, and then if you take the Gilman's reagent and react it with another alkyl halide, which is this one, right? We have 1, 2, 3, 4, and then a Br attached here, and then you treat it with CH3 to copper lithium. Remember, one of the CH3 groups gets attached to this chain, so you actually end up in formation of pentane, and then your side products are CH3 Cu plus Li. Okay, if you want, we can put a color to show that the one of the CH3 groups. Okay, so this is a CH3, so one of the CH3 groups gets attached to that carbon chain, and then the other CH3 remains with the copper. Next slide is again, just talking about the utility of organometallic reagents. Then finally, in this chapter, we are talking about oxidation and reduction in organic chemistry. So we will deal with a lot of reactions in future where we will see oxidations and reductions. So in organic chemistry, oxidation occurs when a carbon or a hydrogen that is connected to a carbon atom in a structure is replaced by oxygen, nitrogen, or halogen. So that means you are reducing the number of carbon-hydrogen bonds, but increasing the number of carbon-oxygen or carbon-nitrogen or carbon-halogen bonds. Sometimes it may not be very easy to locate the oxidation or reduction by loss of electrons in organic chemistry as it was in case of inorganic. So that's why you may want to look for what kind of bond changes have happened, right? So if you go from a carbon hydrogen bond that is replaced by a carbon oxygen bond, then that means oxidation has happened. Okay, so in a nutshell, we can say that if going from reactants to the products, you see that there is loss of hydrogen, and or either you gain or along with the loss of hydrogen, you gain in oxygen, nitrogen, or halogen, then that is a oxidation. And just reverse of that, that if you gain a hydrogen and you lose an oxygen, nitrogen, or halogen, then those are reduction reactions. Okay. So for example, in this case, see, we have lost a carbon-hydrogen bond, right? So you took a halogen, like a hydrocarbon, reacted it with chlorine. So that halogenation of alkane reaction is actually an oxidation because you replaced a carbon-hydrogen bond with a carbon-chlorine bond, right? So you have loss of hydrogen, right? Loss of hydrogen and gain of a halogen. So that is an oxidation. Now in this case, what has happened? See, you have lost a halogen and you have gained a hydrogen. So this happened with our Grignard reaction, right? So we took a haloalkane and we reacted with the magnesium, we get Grignard's reagent. And then when that is treated with a proton source like water, you end up in the formation of alkanes. So this is a reduction reaction. Some more examples here of oxidation and reductions. When we go from a double bond to a carbon halogen bond, right? So we have gained carbon halogen bond, so it is a oxidation. Here we have gained a carbon hydrogen bond. See, we had only 4 carbon hydrogen bonds. Now we have 6 carbon hydrogen bonds. So we have gained a carbon hydrogen bond, or we have gained 2 carbon hydrogen bonds, so it has to be a reduction. And finally, this one, if you look, you have gained a carbon hydrogen, but at the same time, you also have gained a carbon halogen bond, right? So this will be a reaction which is neither oxidation nor reduction. Okay? You should be able to recognize oxidation and reduction reactions. This is an oxidation level where you can see that this here we have the lower levels of oxidation, and as we go across this scale, we see the higher oxidation levels, right? So alcohol is at a lower oxidation level, but if you make it into a like an aldehyde, this is a formaldehyde, so that becomes a higher oxidation level. Then we have carboxylic acid, which again is a higher oxidation level, and then finally carbon dioxide, right? So you can see how the stepwise oxidation scale is increasing. Finally, we have an example here to see if we can solve this to understand oxidation and reduction. So if you look, we have going from an aldehyde to an alcohol, right? So we are going from a higher oxidation level to a lower oxidation level. So this is actually a reduction reaction, okay, reduction. The next one, if you look, we are again going from a lower oxidation level to a higher oxidation level. So this is again an oxidation reaction. Okay, so see, we have gained a carbon oxygen bond. Remember, gaining a carbon oxygen bond is an oxidation reaction. Okay, and then next one, some more examples. Going from alcohol to an aldehyde, so we are going from a lower oxidation to a higher. So this is an oxidation reaction. This one, if you look, we have neither gained nor lost. So this is neither an oxidation, right? Neither an oxidation or a reduction. Okay, nothing has happened. And here again, if you look, this is actually a reduction reaction because you have taken a carbon halogen bond and changed it into a hydrocarbon, increasing the number of carbon hydrogens. So this is a reduction reaction. So that summarizes the reaction. So there is one more. Actually, I'm going to ignore this first part, but we can solve from for B and C. Um, Here what have we done? We have taken an alcohol and turned it into an alkyl halide. Remember, OH to Br. This is a secondary alcohol to a secondary alkyl halide. The best reagent that would work here is PBr3. And then to go from here to here, the reagent would be, so you can turn it into a or you can do a Gilman's reagent, right? Remember, so CH3 twice copper lithium, right? This is a Gilman's reagent, and you can actually get rid of the bromine and put a CH3 group over here. So this, I'll put the color here to show that one of the CH3 groups has come from our Gilman's reagent. Okay, and yeah, so it's just telling me that first one is this, but we will ignore that part. But the second one is PBr3, and then there is the Gilman's reagent. Okay? So that completes the discussion of chapter 10. I will, in a separate video, solve the chapter 10 worksheet so that you can understand how to work out problems in this chapter.